Okay, let's crank out the rest of carbohydrates. So we were up here. Let's go back. So we're all on the same page. Sodium glucose transporter into glut glucose transporter. So now we are in the blood. We've made it to the liver. And we are coming back strong as a glucose molecule. Okay? That's where we are. Now, this is where the G's start. Oh yeah, the G words. There's a bunch. This thing that looks like a cookie is actually your pancreas, right? The islet of Langerhans. There's alpha and beta cells here. We'll get to that. Don't you worry. So, what happens when you have increase glucose? Look at that. You're going to glycogenesis. You're going to make some glycogen and you're going to store it. Okay? Decreasing blood sugar. All right? When you need it, you're going to break down that glycogen. It's going to go back into glucose and it's going to increase your blood glucose. So we have this glucose to glycogen situation. We have insulin and glycagon. I know. I did not do this with the G words, so it is not my fault. Insulin is what helps you ingest glucose. Glucagon is what breaks down your glycogen. I didn't do it. To make glucose from your glycogen, which is your starch flour of storage. And that some of those processes are called. Let's go here so we can absorb the situation. Glucose. This is just a way I have seen it done and I think it's helpful. Glucose is the box. Glycogenesis. So gen, beginning, like Genesis, the book in the Bible. Glycogenesis, building. So you have a molecule of glucose, you want to store it, you use the process, glycogenesis. You use, then glycogen is the starch flour of storage, right? This is how you're going to store it in this big pallet. When you want to break that down into smaller pockets, you're going to use glycogenolysis. Lysing, like when you lyse a cell, it means splitting or breaking. Okay? Glycogenolysis breaks it back down to glucose and puts it in your bloodstream. Okay? An alternative pathway, gluconeogenesis. I'm not even kidding. Glucose molecule. New birth. So you're making glucose in a slightly different way. And that is also going to get you a box of glucose. There's a bunch of these words. You just have to look at the sheet and try and work through them because you have enzymes, you have storage molecules, a lot is going on there. Okay, let's zoom in on the pancreas for a minute. So all of this lovely bile situation, ducts, this is going to break down your lipids and your proteins. We're not there yet. Also, we need to take a moment and appreciate that your pancreas, your amazing pancreas, is both an exocrine and an endocrine gland. An exocrine gland gives something right next to it. So this is your bile, right? We're making the bile appear in the liver, stored in the gallbladder, coming down right here. So it's just delivered right to where you want the thing. An endocrine gland is going to release it into your bloodstream everywhere. Epinephrine, and in this case, insulin. So your pancreas is going to release insulin everywhere. Okay, so it's both an exocrine with the bile and an endocrine with the insulin. That's cool. Let's zoom in further to our amazing pancreas. Okay, so our pancreas here we are very specifically going to talk about the beta. See, here's a little beta. We have alpha, beta cells. We are just going to talk about the beta, okay? Because that's going to release insulin into our bloodstream. Now, once again, I'm going to show you the real picture. Mine's going to look just like this. Exactly the same. Okay, we're going to come back to this picture when we draw our own. Now, I can do it. If I can do it, you can do it. So draw your blood cell here, then draw a little black box. Okay, we got glucose into the bloodstream from our small intestines. See the previous video. We used Sigalt, we used Glut, we used a sodium-potassium pump, and now we're in the blood. We've gone to the liver. Okay, we've gone up to the liver and we've come back to the pancreas. Okay, this is not just like boom, boom, boom. We've gone to the liver and come back to your pancreas. Specifically, your islets of Langerhans. You got to say it like you have a German accent, okay? These are our beta cells. So here's our glucose. It's going to come in with our buddy glut. It's just a glucose transporter. Okay, awesome. Glucose entering through our friend and yours, a glucose transporter. What's it going to do? Do you remember we talked about in the other one that those cells could not use glucose as an energy source because it would just be like me working at Krispy Kreme. I would just eat all the donuts. Here, we do have our beta cells using it not only as a source to make ATP, but it regulates the whole cell. It's crazy. It's super fun. It's like I work at Krispy Kreme, but when I eat all the donuts and get sick, it triggers something. Okay? So, our glucose molecule comes in here to the mitochondria. We already know everything that's going to happen there. It's going to make, through glycolysis and the Krebs cycle and cellular respiration, we are going to make a bunch of ATP. 36 to be exact, right? We're going to make a whole bunch of ATP. That magical ATP is going to go up here and it's going to open this potassium gated channel. It's gated. This is a gate. It looks like a gate. It looks like a gate, right? It hinges right here. That potassium channel is going to open when there's a bunch of ATP, okay? It's going to open this potassium channel, okay? Now, what else this is going to do is change the voltage. It's going to change the ion concentration. It's going to change the electrons, the electricity in the cell, okay? See, these are my little ions here, and that's going to open a voltage. See how I use the word voltage like in electricity? A voltage-gated calcium channel. What? Don't panic. Let's go back in. Glucose comes in through glut, enters the mitochondria, makes a bunch of ATP through cellular respiration. That opens a potassium-gated, that's a gate, changes the electricity in the cell, the voltage. That voltage-gated channel lets calcium in, okay? So who cares? Trust me, it's coming. The big reveal is coming. You've got calcium, a bunch of calcium in here. That's going to bind, what is this? It's insulin. What? And that's going to trigger this insulin to exocytose. It's going to just kind of puke it out. It's going to just like spit it out. It's going to exocytose this insulin into your bloodstream. What? Yes. One more time. Glucose in through our buddy glut, making the mitochondria, right? In the mitochondria, we're making a bunch of ATP. That ATP opens a potassium channel. That's a gate. That potassium and ATP change the voltage. Opens a voltage calcium channel. That calcium channel triggers your insulin to come up here in little packets and exocytose from the cell. Now, see this one? The same. Let's look at it from people who may or may not know how to draw. Glut. Here's our glucose transporter coming in here, doing some glycolysis through mitochondria, right? We got the ATP. Where's the ATP going? To open this potassium channel. Okay? What's that doing? It's going to bring in a bunch of potassium. That's going to depolarize, aka change the voltage of this calcium channel because it's a voltage-gated calcium channel. That's going to let a bunch of calcium in, and that calcium is going to, here is our insulin, and it's going to exocytose the insulin out into the bloodstream. This picture looks exactly the same as my picture. Okay? Now, there we go. We did that. You should have this drawn. I'm going to give you this big picture. Okay, so now we have glucose in our cells. What are we going to do with it? I'm going to make another video for that so that we can take a breath. If you want to take a breath from this one, we'll make another video on glucose.